Hey everybody, today you're going to talk about the Gram-Schmidt process with, shockingly, me. Big idea. We want to build orthogonal bases for our subspaces. First example, we're going to try and start simple. We have a basis of R2, but we want to use it to create two orthogonal vectors so that we can have an orthogonal basis. So, real quick, I want you guys to recall that if we have two vectors, u and v, then we can say that the projection of u onto v is called u parallel. And that's because that's the piece of u that is parallel to v. And then we also have u perpendicular is equal to u minus u parallel. So that would be the part of u that's perpendicular to v. So we can take advantage of this. We can say, let's just start with v, and then if we go find u perpendicular, then we'll be good. We'll have two orthogonal vectors, both in the same space, because u perpendicular isn't going to go to a different space than u. And so we'll have a basis for the right space. So let's say that v is our first vector, 2, -1, and u is our second vector, 1, 1. Let's look for u parallel. So u parallel would be equal to the projection of u onto v. And so then we're going to have u dot v over v dot v all times v, and that'll give us u parallel. So it's real quick, we do the dot products, we get 2 minus 1, then 1 plus 1 v. So that'll be, no, v dot v is going to be, there we go, 4 plus 1, there we go. So that is 1/5. So 1/5 of v would be 2 -1 like that. So 2/5, -1/5. And there's u parallel. And now we just need to find u perpendicular. So that would be u minus u parallel, which is 3/5 and 6/5. So then our orthogonal basis is going to be v, and the part of u that was perpendicular. So bear in mind that length has nothing to do with orthogonality. And so if we are offended by these fractions, which I am a little bit on the inside, you can just multiply by a scalar to get rid of them. Because again, if you multiply by like 5 and get 3/6, you've done nothing to change the direction. You've just changed how far in that direction it goes, which means we still have orthogonality preserved. Everything is fine. You can stop here because you don't like doing extra work, or you can keep going because it makes you happy on the inside. Okay, let's try this again for a bigger subspace. So we've got 1, 1, 1, 0, 1, 1, and 0, 0, 1 is a basis for R3. Can we construct an orthogonal basis? Yes, we can. Otherwise, I wouldn't be asking. Let's start with the first two. We're going to say x1 is where we're going to start. And then we want to find x2 perp, because we know that's going to be orthogonal to x1. So let's find x2 parallel, which is going to be projection x1, x2. Okay, so that's going to be x2 dot x1, x1 dot x1, x1. So then that's going to be, let's see, just 2 up top, and then 3 on the bottom, and then x1 is 1, 1, 1. So just a 2/3 vector. And then x perpendicular, x2 perpendicular is just x with the missing parallel part. So x2 would be 0, 1, 1 minus this 2/3 vector. So that's negative 2/3, and then a positive third and a positive third. All right, so that's one vector. So what about our third vector? We need it to be orthogonal to x1 and x2 perpendicular. So orthogonal and orthogonal to those guys. So what we're going to think about now is, what if it's just orthogonal to the entire subspace, right? So want x3, or we'll say the piece of x3, that is perpendicular to the span of x1 and x2 perp. And we're like, oh, we already learned how to do like finding a vector that is perpendicular to an entire space. So let's go ahead and use that now. So I'm going to flip to the next page. So we're going to say that x3 perp is going to be x3 minus the part that's parallel. And then we're going to use what we know about projections to find that parallel part. So projection onto the span of x1 and x2 perpendicular. x3. And then let's write out the definition of that projection. So that's x3 dot x1, x1 dot x1, x1, plus x3 dot x2, x2 perp, x2 perp dot x2 perp. Yep. All times x2 perp. Okay. We're about to take a lot of dot products. So x3 minus, and then let's see, x3 dotted with x1 is going to end up giving us a 1. And then x1 dotted with x1 is 3. Because remember, x1 was the 1, 1, 1 vector. And then that's times x1. And then distributing that minus sign, right? So minus, and then x3 times x2 perp. I promise that is also a 1. And then that's a x2 perp times dot x2 perp ended up being 2. x2 perp is equal to, and then that's going to look like 1, 1, 1 minus 1/3, and then, no, x3 is 0, 0, 1. x1 was 1, 1, 1. There we go. Minus a half, and then that's negative 2/3, 1/3, 1/3. And then that ends up equaling, let's see, that is a 0, and then a 1/3 minus a 1/6 is a negative half, and so that's like 1 minus a half for the bottom one, so positive half. Okay, so then our orthogonal basis for R3 that came from the vectors we were given is 1, 1, 1. So it's just that first one again. And then negative 2/3, 1/3, 1/3. And 0, negative a half, and a half. Parenthetically, or we could not look at all those gross fractions and we would get like something like this. There we go. So that is also perfectly valid choice for an orthogonal basis. So what we're doing though is we're doing something intuitively that has a formal name called the Gram-Schmidt process. And this is what it looks like. So you take your so you've got your basis. We're going to create an orthogonal basis in the following way. The very first vector, we just say, well, that's our starting point. Let's take him. And then we take V2 and we say that is x2, but only the part that's perpendicular to what we had before. Right? Because this right here is x2 parallel. Equivalently, I've got over here, right? Because that's x2 minus the projection of x2 onto, and we're going to use v1, not x1, just so that we can build and keep track of. Okay, and then the very next one, here, I'm going to start here. We're going to say V3 is X3 minus the part that was parallel to what we already had. That would be the projection onto the span, so minus the parallel part. And then if we just use the definition of projection, we get back to that piece right there. It should look very familiar from what we had on the previous slide. And you do that all the way down. We're going to get rid of the part that's parallel by subtracting off the projection, and that leaves us, when we plug in the definition of projection, with xp minus all the little bits that were parallel. Okay, so again, we just did that twice using intuition. So big idea for Gram-Schmidt, you take any basis, you do some Gram-Schmidt, and you get out an orthogonal basis. Quick note, we can actually get an orthonormal basis very easily if you just do Gram-Schmidt and then you normalize all the vectors in your result, because then it would be orthonormal. Okay, so let's take a moment, let's see this work. So our next example, we have a plane that is being spanned by two vectors, and we want to find an orthonormal basis instead of the two vectors that they've given us. So here we go. We'll say that this is x1 right here, and this one is x2. And then that means we can say that V1 is just going to be x1, and V2 is going to be equal to x2 minus x1 dot V1, V1 dot V1 times V1 from Gram-Schmidt, because that's just going to get rid of, x2, not x1, because that'll get rid of the parallel part of x2. So here we go. Let's do some dot products. So x2 V1, that is going to be -1 plus 4. And then V1 dot V1 would be 1 plus 4 plus 4. V1. Okay, so plugging in our vectors and simplifying, that's going to look like -1, 0, 2 minus 1/3. V1 is 1, 2, 2. And then the result is going to be a bunch of fractions. Ugh. -4/3, -2/3, +4/3. There we go. So we have our basis, we have our V1, we have our V2, but it said orthonormal, so let's normalize it real fast. So if we normalize V1, we're going to need the length of V1, which is going to be the square root of V1 dot V1, which is going to be the square root of 1 plus 4 plus 4. So that's a 9. So square root would be 3. And then for V2, we've got 16 over 9 plus 4 over 9 plus 16 over 9 square root. So that'll be a 36 over 9, which is square root of 4, so 2. So then our unit vectors, so U1 would look like this. So then we just take V1 and we divide by 3. So that is 1/3, 2/3, and 2/3. U2, Landon. So U2 is going to be our normalized V2 vector, which is a half of V2, which I can just plug that in. So 1/2 actually makes our fractions, I don't know, makes me feel a little bit happier. There we go. So our orthonormal basis looks like 1/3, 2/3, 2/3, -2/3, -1/3, 2/3. Okay, so there we go. Orthonormal basis. Now, let's do kind of an interesting example. I want an orthogonal basis for R4, but I specifically want it to contain these two vectors. So I didn't give 4 vectors this time, so we're going to have to go and find the other 2 vectors somehow. So first things first, if it's going to be an orthogonal basis for R4, and it's going to contain those 2 vectors, then those 2 vectors better be orthogonal. So let's check them. We're going to take the dot product. And see that ends up being 2 plus 0 plus 0. Did I see that I didn't change it. That was supposed to be a 1. Because if it wasn't a 1, it wouldn't be orthogonal, and we would be, in trouble. Okay. But if it is a 1, we're fine. Everything's good. So then that would be 2 of our vectors, x1, x2, and then we need 2 more vectors, but we need them to be orthogonal to the 2 vectors that we already have. Okay, so then we need it to be orthogonal to the space we already could create. So I'm getting somewhere. If I say that V is equal to the span of x1 and x2, what I need is a basis for the orthogonal complement of V. So if I pick a basis for the orthogonal complement of V, that is going to definitely give us the rest of R4, because you have what's parallel to V, and you have what's perpendicular to V, and there are no other directions to go. That's going to give us all of R4. It's definitely going to give us stuff that's perpendicular to x1 and x2, because the orthogonal complement. So let's see if we can find a basis for that space. So how do we do that? Well, let's write out what we want. So we want all vectors y, which is going to be, I'm going to do just like y1, y2, y3, y4. We want all vectors y such that x1 dot y is equal to 0, so that it'll be perpendicular, and x2 dot y is equal to 0. So we want it to be perpendicular to both of those 2 vectors, and then it should be orthogonal to everything in V, because it was orthogonal to the basis of V. So let's go ahead. Let's write down what that's going to mean. So x1 dot y would give us the equation. Let's see, x1 was 2. So 2y1 plus y2, and then 0y3 minus 2y4 would be equal to 0. So that's that equation right there. And then the next equation would be y1, 0y2 plus 3y3 plus y4 equals 0. And that comes from x2 dot y. So it kind of looks like we need to solve a system of linear equations. Golly, if only we knew how to do that. Let's go ahead, let's make an augmented matrix. Okay. And then this actually solves pretty quickly. Let's see. We're going to switch 2 of our rows, which are the only 2 rows we have. And then we'll do R2 minus 2R1. Can never do Gaussian elimination too many times, can we? -6, -4. Okay. So let's take what we've got there. So that means that we have y1 would equal -3 y3 minus y4. y2 equals 6y3 plus 4y4. And then y3 and y4 were going to be free. So then our y vector is going to be anything that looks like, let's see, -3, 6, 1, 0 times y3 plus -1, 4, 0, 1, y4. So then remember, these guys give us a basis for V perp. However, they are linearly independent, but you guys saw on your worksheet yesterday, that does not necessarily give us anything. Give us anything about orthogonality. Okay, so what do we have so far? Let's start trying to construct our basis. So V1 is going to be x1. V2 is going to be x2. And then now we're into, now what? So we've got our basis for V perp, and those are going to be like our remaining vectors that we need, but are they necessarily orthogonal? Sort of. We can say here, let's label this guy y1 and this guy y2. They are orthogonal to x1 and x2. That was by construction, right? I said right here, boom, boom. I need vectors so that they're going to be orthogonal to x1 and x2, please. So that means y1 and y2 right here, those guys are going to be orthogonal to x1, x2. So let's take the first one. There we go. So now we have 3 of our 4 basis vectors that we need. And then our very last one, he's linearly independent from y1, but he's not necessarily orthogonal, but that's not a problem because we have Gram-Schmidt. So really, we only need to use Gram-Schmidt here at the very, very end of the process. So V4 is going to be y1, no, y2, minus the part that's parallel to y1. So that would be y2 dot v3, v3 dot v3, v3. You're like, oh, but Gram-Schmidt, shouldn't you be doing, you know, all of them? Like y2 dot v2 over v2 dot v2, v2, and then the other one? Well, that means I would be doing y2 dot x2, which means it would be 0. Because remember, I already said y2 is constructed to be orthogonal to x1, x2. And so the same thing with the term over here, y2 dot v1. That would also be 0. So no, I do not really care about any of that stuff. I just want the, I just need to orthogonalize it with respect to the other y vector. So let's go ahead and do that. Let's grind that out. So y2 dot v3, that is going to be 27. And then v3 dot v3, which is just y1, that's going to be 46. It's 9 plus 36 plus 1. Yep. And then times V3. So let's go ahead. Let's plug these numbers in. So Y2 is -1, 401 minus, and then 27 times, well, I'm not even going to do it, 27 over 46 times -1, 401. And this is where you go get a calculator, because this isn't really worth trying to do in your head. -1 minus 27 over 46 times -1 ends up being 35 over 46. 22 over 46. -27 over 46. And 1. You may have your Jello. I mean, you guys can have Jello too. I can't stop you. Okay. There we go. Orthogonal basis is going to be V1, which was just x1. So 2, 1, 0, -2. And then V2, which was just x2, 1, 0, 3, 1. Y1, which would be -1, 4, 0, 1. Or, ooh, that was Y2. -3, 6, 1, 0. And then Y4, I'm going to choose to multiply V4 by 46, because I don't like writing fractions. It's gross to look at. Goodness, you're going to finish this class and you're going to be like, well, we know Gracie hates fractions. But anyway, there you go. That is an orthogonal basis, not the orthogonal basis, because obviously you could sub out those vectors and it would be a different basis, but still orthogonal. So it's one of the choices, and it's the one that I have picked. Okay. So Gram-Schmidt is mostly used to find orthogonal bases, but it can be used for other purposes, even though the previous 4 examples have all been finding bases. For example, we could use it to determine if vectors are linearly independent, which I'll let you guys discover that one on your homework. And you can also use it to find the distance between a vector and a subspace, which I've got a very simple example sitting right here. Let's draw this out real fast. Let's say right here, we've got our x vector is like this. This is our x vector. And then our subspace would look like that. And then it would be stretched out like that. So this is V. So in order to find the distance between x and our subspace V, which that looks a lot like a negative V and it bothers me, you want to find the closest vector in V to x. So right here, that's going to be this guy. But oh wait, that's just x perpendicular. And we can find that doing like the whole Gram-Schmidt thing. So let's go ahead and do this using Gram-Schmidt, even though it's a little bit unnecessary in this case, but we're going to do it. Okay. So you start, you say V1 is going to be the vector that we're taking the span of. That way we can use it to subtract off the parallel component of x. So then V2 is going to be x minus x dot V1, V1 dot x, or V1 dot V1 times V1. Remember, this is just the part of x that is parallel to the subspace. And then V2 would then be the perpendicular part. So here we go. We plug these numbers in, get a 0, or yes, x is 0, 2, minus dot product is going to be a negative 2 over a 2. 1, negative 1. Is that right? Yes. Okay. So that's just going to be like 0 plus 1, which is 1, and then 2 plus negative 1, which is a 1. So then now we have the vector x perpendicular. So if we just take the length of x perpendicular, we'll know exactly how far away x is from our subspace V. That would be the square root of 1 squared plus 1 squared, root 2. And that's a number I can live with. Okay, and then you guys will have the chance to practice this on a bigger subspace on, I think it's the exam review. But that's all I've got for you guys right now. Thank you. Bye.